Hello everyone, my name is Xinyu Liu. This is a video recording for ITCS 2026, and today I will be talking about our paper Near Optimal Sparsifiers for Stochastic Knapsack and Assignment Problems. This is a joint work with Shadin Dugmi and Yusuf Hakan Klaichi, and we're all from the University of Southern California. The knapsack and the generalized assignment problem are both very familiar problems, so I will only briefly recall the standard setting. Then I will give more details about their stochastic variants, as well as explain what we mean by sparsifiers in this context. Let me start by recalling the definition of the generalized assignment problem, where the knapsack is a special case of it. We're given the ground set of items denoted by E, and the size of E is n. There are m knapsacks, and each knapsack J has a capacity C sub J. Each item I can be assigned to different knapsacks, and its value and weight may depend on the knapsack. Concretely, if item I is assigned to knapsack J, it gives value V sub ij, and consumes weight W sub ij. The goal is to choose disjoint subsets of items and one subset for each knapsack, so as to maximize the total value. At the same time, for each knapsack, the total weight of assigned items must not exceed its capacity. Equivalently, we can view GAP as defining a family of feasible item sets. A set S is feasible if the items in S can be assigned to knapsacks without violating any capacity constraint. For any item set S, we use f of S to denote the maximum total value obtainable by a feasible assignment of S. This formulation will be convenient when we later discuss GAP's stochastic version and sparsification. Now let me describe the stochastic variant of the generalized assignment problem. In this model, each item is independently active with some fixed probability P, where P is a number strictly between 0 and 1. This randomness induces a random active set, which we denote by R. And R is a subset of the ground set E. You can think of R as the set of items that actually show up. The key difference from deterministic setting is that we do not know the active set in advance, and our decisions must be made with respect to R. Our goal is still to choose disjoint subsets of items, one subset for each knapsack, but now only from the active set. Formally, we want to choose subsets S1 through Sm, all contained in R, such that their union is a feasible set in the original GAP sense. Among all such choices, we aim to maximize the total value, which we denote by f of S. This stochastic formulation is the starting point for discussing how to interact with randomness. In this work, we considered a query model. Here, decisions must be made based on the active set of items. We interact with randomness by querying items one by one. A single query simply tells us whether an item is active or not. Now, in principle, we could query all items and fully reveal the random set R. But in many applications, this is costly or even infeasible. Queries may take time, money, or consume system resources. So acquiring the complete information of the stochastic space is often inefficient or unrealistic. Therefore, our goal is not to query everything. Instead, we want to query only a small or sparse subset of items, while still preserving near-optimal solutions. This is exactly the motivation behind sparsification. To make this more concrete, let me illustrate this idea with an example. Imagine we're designing a recruitment strategy for a startup tech company. We have limited interview time and a limited salary budget, and our goal is to hire a team of engineers that maximizes total impact. There are different types of candidates. For example, we may try to hire senior engineers or instead focus on junior or mid-level engineers. Hiring senior engineers typically requires more time for interviewing, negotiation, and convincing, and they also come with higher salary expectations. At the same time, their expected impact is also higher. In contrast, junior candidates are easier to reach and cheaper to hire, but their individual impact may be smaller. Importantly, recruitment is inherently stochastic. Every candidate is essentially a maybe until the interview process is completed. We model this by assuming that each candidate is successfully convinced and therefore available to hire with some fixed probability P. Crucially, we only learn whether a candidate is available after we have spent the time to interview and negotiate with them. In other words, each interview is a query. It costs time and involves whether the candidates join or not. This leads to a natural strategic question. Should the recruitment team spend more effort trying to hire a few senior candidates, or should they focus on many junior candidates instead? Now, notice that this hiring problem fits naturally into our framework. The time spent interviewing corresponds to a query cost. The salary budget induces a capacity constraint, just like in the knapsack problem. And the impact of a hire corresponds to the valuation. We can further view this hiring problem as an assignment problem. Imagine that the startup has multiple departments such as backend, front-end, data, and infrastructure. Each department has its own budget and needs. In this case, hiring a candidate is not just a yes or no decision. Different candidates may generate different level of impact depending on which department they are assigned to. Our objective is to choose a set of candidates who are available after the interview process, together with an assignment to departments so as to maximize the total impact, subject to the department's budget constraints. This is exactly the structure of a stochastic generalized assignment problem. But since interviews are costly, the central question becomes, which candidates should we query so as to still obtain the near-optimal hiring outcome? Motivated by the hiring example, we now formalize the sparsification problem. Given a stochastic assignment problem, a sparsification algorithm selects a possibly random query set, which is a subset of the item set. Intuitively, this corresponds to the set of candidates that we choose to interview. The goal of sparsification has two main objectives. First, an approximation guarantee. We want that after querying the items in the query set and observing which of them are active, we can compute a solution from our queried active set whose expected value is within a constant factor, say alpha, of the optimal value when all active items are available. Second, we want to ensure that the query set is small, which captures the fact that queries are costly and we cannot afford to query everything. At this point, a natural question arises. What is the right notion of sparsity for assignment problems? To address this, let me first take a short detour to explain how we measure sparsity in our framework. To define what it means for a query set to be sparse, we take a polyhedral viewpoint. Intuitively, we want a notion of sparsity that reflects how many feasible solutions are still captured after we restrict attention to the queried set. Now we define the feasible polytope. Recall that for a general assignment problem, a set of items is called feasible if there exists at least one valid assignment of these items to knapsacks that satisfies all capacity constraints. For each such feasible item set S, we consider its indicator vector and we take the convex hull of all such indicator vectors. We denote this polytope by P sub f. By construction, the vertices of this polytope correspond exactly to feasible item sets. With this polyhedral view in place, we can now define the polyhedral sparsification degree. Given the query set Q, we define its sparsification degree as the smallest scalar d, such that after scaling down by a factor d, the query set can be expressed as a convex combination of feasible solutions. This gives us a clean way to quantify how large a query set is relative to the structure of feasible assignments. To make this definition concrete, let me walk through a very simple example. Consider a single knapsack problem. The capacity is 1 and there are 2 items. Each item has weight 1 and value 1. Since the capacity is 1, we can choose at most one item. So the feasible item sets are choosing item 1, choosing item 2, or choosing nothing. The shaded triangle here is exactly the feasible polytope P sub f. Now, suppose our query set Q contains both items. That is, the indicator vector of Q is the point 1, 1. This point lies outside the feasible polytope since we cannot take both items at once. However, if we scale it down by a factor of 2, the point 1/2 times 1, 1 lies inside the polytope. Equivalently, Q lies inside 2 times the feasible polytope. The polyhedral sparsification degree D of this query set is 2. With both notion and example in place, we can now give the formal definition of a polyhedral sparsifier. An algorithm A is called an alpha approximate sparsifier with degree D if, on every problem instance, it outputs a possibly randomized query set Q, which is a subset of E, and it satisfies 2 conditions. The first condition is the approximation guarantee, which we have essentially seen before. The second condition is the polyhedral feasibility. It requires that 1 over D times the indicator vector of Q lies in the feasibility polytope P sub f. And importantly, this must hold for every realization of Q if it is randomized. So in summary, alpha measures how well we preserve value, and D measures how sparse the query set is in this polyhedral sense. Before presenting our results, let me briefly place our work in the context of existing literature. The notion of sparsification originates from work on stochastic matching. In stochastic matching, we're given a graph where edges appear randomly. The goal is to query a small subset of edges, observe which of them are active, and then compute a matching with high expected total weight. This problem has been extensively studied in general graphs and bipartite graphs, as well as in both weighted and unweighted settings. This line of work assumes that every vertex will be instant to at most D many edges, where D is the sparsification degree in this domain. Later, sparsification ideas were also studied for more general packing problems, such as stochastic matrix optimization. In that setting, the sparsification degree is the size of the queried solution divided by the rank of the matroid. Our contribution is that we provide a single unified framework based on polyhedral structure. Our polyhedral sparsification degree recovers all of these notions exactly in their respective settings, but is strictly more general. In addition, it naturally captures assignment problems where the structure of feasible solutions can vary a lot. As a result, our framework applies a broad class of stochastic packing problems. Now let me state our informal main result. For any epsilon between 0 and 1/6, and any activation probability p between 0 and 1, there exist efficient algorithms for the stochastic knapsack and the stochastic generalized assignment problems with the following guarantees. First, the algorithm achieves a 1-6 epsilon approximation to the stochastic optimal. Second, it produces a query set with polyhedral sparsification degree polynomial in 1 over epsilon and 1 over p. Importantly, this degree is independent of the problem size, such as the number of items or the number of knapsack constraints. Let me also briefly clarify 2 properties of our algorithm. First, our algorithm is deterministic, meaning that for a fixed problem instance, it always outputs the same query set Q. And it is also non-adaptive, meaning that the entire query set Q is chosen upfront. In particular, the algorithm does not query an item, observe whether it is active, and then decide which item to query next. Finally, a small but important remark. A small sparsification degree does not imply that the query set itself has small cardinality. For example, if all items have very small weight, the query set may still contain many items. Later in this talk, I will focus on knapsack sparsifiers. The result for the generalized assignment problem follows similar ideas but require more technical proofs and are omitted here. I want to highlight the core insight behind our approach. The idea is to query enough substitute items so that every possible realization is adequately covered. More concretely, consider any realization of the active set R and any item or group of items that the optimal solution on R might use. We require that the intersection of the query set Q with the realization R contains either the item itself, or a suitable substitute or a group of substitutes that has similar value and no larger total weight. If this condition holds, then even if the original item is not queried, we can replace it using queried items without significantly hurting the total value gain. As a result, the optimal solution for R can be approximately reconstructed using only the queried items. To implement the substitution idea I just described, we use a value-based bucketization scheme. Let me explain what this means and why we define the buckets in this way. We partition items according to their values. The first bucket contains items with value between 0 and L. The second bucket contains items between L and L times 1 plus epsilon. In general, each bucket grows multiplicatively by a factor of 1 plus epsilon until we reach the maximum item value. This defines K buckets in total. From each bucket, we query items until the total queried weight reaches a polynomial factor in 1 over epsilon and 1 over p times the knapsack capacity C, or until the bucket is exhausted. By standard concentration inequalities, querying this much weight is enough to guarantee that, with high probability, the total weight of queried active items in each bucket exceeds the knapsack capacity C. This ensures that, if the optimal solution draws items from a bucket, we are very likely to observe enough active substitutes from the same bucket. The upper bound of the buckets is said to be equal to the maximum item value. This ensures that all items, especially the most valuable ones, are covered by the bucketization. The lower bound L is defined as epsilon times p times the maximum item value. This choice guarantees that the contribution of each item in the first bucket is at most an epsilon fraction of the expected stochastic optimal. With these choices, the total number of buckets K is polynomial in 1 over epsilon and 1 over p. Putting everything together, we ensure that this scheme has the polyhedral sparsification degree polynomial in 1 over epsilon and 1 over p. Based on the value-based partition, we assign an index to each bucket. We define bucket B0 to contain all items whose value is at most L. For each K at least 1, we define bucket B sub K to contain items whose value lies between L times 1 plus epsilon to the power K minus 1 and L times 1 plus epsilon to the power K. This gives us a sequence of buckets ordered by increasing value. With this notation in place, we classify the buckets into two types. The bucket B0 is called the small value bucket, and all remaining buckets from B1 through B capital K are called the large value buckets. This distinction will be important because we handle small value and large value buckets using different algorithms as well as different arguments in the analysis. Let me describe how we query items in each case specifically. First, consider the small value bucket, B0. By definition, all items in this bucket have value at most L. In this case, it is natural to compare items by their density, that is, value divided by weight. So for the small value bucket, we sort items by density in non-increasing order, and we query a prefix of this ordering. Next, consider the large value buckets from B1 through B capital K. Within each such bucket, all items' values are already within a factor of 1 plus epsilon of each other. Therefore, to obtain a valid substitute, we only need to find items with smaller weight. So for each large value bucket, we sort items by weight in non-decreasing order, and again querying a prefix. Given our knapsack sparsifier, we now state its performance guarantee. For parameters epsilon in the interval 0 to 1/3 and p in 0 to 1, we show that our bucket-based sparsifier for the stochastic knapsack problem achieves the 1 minus 3 epsilon approximation to the stochastic optimum. In addition, the sparsification degree is bounded by a polynomial in 1 over epsilon and 1 over p. This result extends to the generalized assignment problem as well. The similar bucketization idea applies, and we obtain a similar approximation guarantee and sparsification degree. For the analysis, as the sparsification degree bound already follows directly from how we construct the query set in each bucket, here I will briefly sketch the proof of the approximation guarantee. The proof uses a charging scheme. For each bucket, we'll look at the items used by the stochastic optimum and try to charge each such item to a suitable substitute inside the query set. The key observation is the following. By construction and standard concentration inequalities, with high probability the queried active items in each bucket have total weight exceeding the knapsack capacity C. This means that within each bucket, we have enough queried active items to serve as substitutes for optimal items. We now analyze the charging argument separately for small value and large value buckets. For the small value bucket, all items have value at most L. These items are queried in non-increasing order of density. We can therefore apply a standard greedy by density argument to select a group of queried items as substitutes. Since every item in this bucket has value at most L, the total greedy loss incurred in this bucket is bounded by L, which is no larger than epsilon times the expected stochastic optimum. Next, consider the large value buckets. Within each such bucket, all items already have values that are close to each other within a multiplicative factor of 1 plus epsilon. Here, we query items in non-decreasing order of weight. As a result, for any optimal item that was not queried, with high probability there exists a queried item in the same bucket with smaller weight, which has not been charged yet, and thus can serve as a one-to-one substitute without violating feasibility. Combining these two cases across all buckets, we can approximately reconstruct the stochastic optimum using only queried items, which yields the claimed 1 minus order epsilon approximation. The same high-level charging argument extends to the generalized assignment problem, with additional technical details. To conclude, our main contribution is that we propose a unified polyhedral sparsification framework for stochastic packing problems. Using this framework, we show that both the knapsack problem and the generalized assignment problem admit 1 minus epsilon approximate sparsifiers, with sparsification degree polynomial in 1 over p and 1 over epsilon, and notably independent of the problem size. Finally, an interesting open question is whether we can design size-independent sparsifiers for general integer linear programs, where the degree depends only on 1 over p, 1 over epsilon, and intrinsic structural parameters of the problem. Thank you very much for your attention.